TTL Computer 2. Today we'll be taking a look at numeric representations in TTL Computer 2 and Pilot. And more specifically, we're going to be looking at fixed point numbers. So let's get into this. All right, so what we're looking at here is just a representation of our standard 16 assigned 16-bit number. And we can see that we have 16 bits 0 through 15. And each bit represents a power of 2. So bit 0 is 2 to the 0 or 1. Bit 1 is 2 to the 1, 2 to the 2, 2 to the 3, all the way on up to 2 to the 15, really. So those are all of our, powers of 2 that can be represented in 16 bits. And this is what's called a 2's complement form. And what that primarily means is we can represent negative numbers in 2's complement form, and the most significant bit we use as the sign bit. So that's our standard 16 signed 16-bit representation, just a plain binary representation uh, in computer systems. And we have our assumed decimal point is right here, right? Is right after the first, right before the first bit is our decimal point, because this represents whole numbers, right? Only integer numbers are represented using this format. Okay, so now let's look at a fixed point format that I've decided to use. And we can see the first thing that we can see is, again, we have 16 bits, bit 0 through bit 15. And we can take a sneak peek ahead and we can see that bit 15 again is we use as our signed bit. So this fixed point format is a 16-bit signed format. And we can see here that the decimal point is not at bit 0, right? The decimal point now in our fixed point representation is right between, right, bit 3 and bit 4. This is our decimal point. So from to the left of the decimal point bits are our integer portion of our number, and to the right of the decimal point represents the fractional portion of our fixed point number. So we can see some similarities here, right? We have our first bit of our integer representation is 2 to the 0. Same thing here. First bit of our integer representation is 2 to the 0, 2 to the 1, 2 to the 2, on up to 2 to the 10. Now, going to the right of our decimal point continues that same pattern, right? 2 to the minus 1, 2 to the minus 2 power, 2 to the minus 3, and 2 to the minus 4 power, right? So that ends up being, this is 2 to the minus 1 is a half, 2 to the minus 2 is a quarter, right? 2 to the minus 3 is an eighth, and 2 to the minus 4 is a 16th. So those are the numeric values for each of those bits. So that's the format, the fixed point format that I've decided to use. Now, this, as the title says, fixed point, the decimal point does not move within our numeric representation. It doesn't move in the straight, binary representation. The decimal point is fixed and always assumed to be here. And for our format, the decimal point does not move. It's always here. So the lower 4 bits are always treated as the fractional portion, and the upper 12 bits are the whole portion. Now, so what's really good about this format is that since they're both 16 bits, we can use the same 16-bit routines that we have to do addition and subtraction. The same methods that we use for the integer, 16-bit integer, we can use that same code to do addition and subtraction on our fixed point numbers. And almost the same for our multiplication and division. We have to do a little bit of pre-processing for our division, and we need to do a little bit of post-processing for our multiplication, but we still are using the same code for our 16-bit integer as we are using for our 16-bit fixed point. Now, while that's true, we can use the same code. We cannot add a 16-bit integer number directly to a 16-bit fixed point number. You cannot do that. So uh, to add the two numbers, they have to be in the same representation. So if we're going to use if we want to add to an integer number with a fixed point number, we have to do a conversion. And to convert from an integer to the fixed point, all we have to do, we see is bits, the 2 to the 0 is here, 2 to the 0 is here. So all we have to do is shift these bits up, right? We can shift this bit up to the bit 4 position, and we fill it with zeros, right? Because we've just shifted up the integer portion to here, and there is no fractional portion, so the fractional portion is going to be 0. So now that we've shifted it up, we can use our addition routines to add those two, add the integer number together with the fixed point number. So one thing to note is when we shifted this up 4 bits, right, we lost these 4 bits at the top, right? 1, 2, 3, 4. Those things shifted off the end. So when we do a conversion, we're losing precision, or we're losing magnitude, right? The same thing we can do in reverse. We can convert a fixed point number to an integer number by shifting the bits to the right this time, 4 positions, right? So that the integer portions are aligned. But in this case, we shifted off the fractional part of the number. So we lost precision. And that's something that we have to deal with, heavily in Pilot. And we'll see that in the second part of our video. So let's go on. So since we have these different representations, we have different numeric ranges for each of the numeric types. For a 16-bit integer, the range is minus 32,768 to positive 32,767. For our fixed point number, we have minus 2048 to plus 2047 is our numeric range for our fixed point numbers. And because of some special, I talked about pre-processing and post-processing on multiplication and division. And because of that processing, our fixed point division range for the numerator is minus 128 to plus 127. And all right, so what we're going to do now that we've introduced this is we're going to look at Pilot, and we're going to see how some of these things impact Pilot. Okay, so we're ready to jump into Pilot, and we're just going to go there, and we're going to do a warm start because I already have a program loaded. And let's just look at that. All right, so this is just a simple program that's using an integer f, starting with 0, and it's just going to display that. And each time through the loop, it will be adding 1/16 to f. And what we can see is 1 divided by 16.0, right, to make that be a floating point division. Now, so where do we get this 1/16? Because the least significant bit in the fractional portion of the fixed point number we said was 2 to the minus 4, which is 1/16. So we're adding, right? We're adding a least significant value each time through the loop. All right, so let's go ahead and let's just run this and see what we get. All right, so by doing that, what are we seeing? Right, so we're going from we're starting out at 0 all the way up to 1, and we're basically iterating through all of the bits, right? We're counting through those lower four bits of the fraction by 1/16th each time. So this is showing us the the numeric value for each of the fractional bit combinations, right? So these are fully the fractional, fractional representations that TTL computer 2 can accommodate using only the four bits, right? We have 0.062, 0.125, right? A quarter, a half, all the way on up to 0.937. So these are the specific values of each of the possible bit combinations in the fractional portion of our fixed point number. If we wanted to have, support a wider range in the fractional number, we would have to add, right? We would have to go to a different fixed point representation. Instead of a 12.4, we'd have to go to an 11.5, right? We would be giving up magnitude again and getting more precision. But I felt this was a good compromise. Gives us a pretty reasonable range of fractional numbers between 0 and 1 that we can represent, again, with a target towards games. Okay, next, we're going to just go to a special version of Pilot that's a debug version. We're going to do a warm start here and take a look at the program I have loaded. So this is just a two-line program. It's going to initialize n to some value, and then it's just going to display what n is. And n is an integer variable. And we see that we set n equal to 1 plus 2 times 1.5. So we can see that 1 is an integer, 2 is an integer, and we're going to multiply that by a fixed point number. And then that fixed point result is going to be stored into n, which is the integer number. So let's just run this and see what we get. Okay, so this debug version is helping us to see what it's showing us what's going on with the type conversions, where we said we can't just add or multiply, an integer number with a fixed point number. We have to go through a conversion process to do that, to convert them into the same type. And that conversion is called a cast in programming terminology. It's called casting. So what's going on here? So this is starting the calculation statement, and all calculation statements start as integer calculations, because integer gives us the most magnitude. It's the largest numbers we can represent. So we're starting to do this process here, and it's going along, starting as 1. Okay, so now it's processed the 1. It's starting to process the 2. The 2 is also an integer number, so that's okay. So now it's trying to do 2 times 1.5. This is a problem. We need to do a type conversion here because the 2 is an integer. We're trying to multiply it by 1.5. So that's what this first thing is saying. It's saying a calculation cast or a calculation type conversion. It's taking the 2 and converting that to be a fixed point 2 to be able to multiply it by 1.5. So it's doing that. It's making that the result is being a fixed point 3. So it's returning the fixed point 3 to add it to the 1. But the 1 is an integer, and it knows it's trying to add it to the fixed point 3. So that's our next type conversion. It says calc cast. It has to convert the 1 from an integer 1 to a fixed point 1. And that's what the calcast is here doing. So it's converting that to a fixed point 1 times 3 is a fixed, right? The result is a fixed point 4. So now we're trying to take the result, which is fixed point, and store that into the integer n variable. But we have to do a type conversion again because the resulting 4 is fixed point. We need to convert that to be an integer. And that's what this is saying here. It's saying the result is being cast to an int, right? And then we see the result here, typing out n, and n equals 4. So that's just to show you there's a lot of complications going on with the fixed point numbers and the integer representations. And Pilot is doing all of this stuff right for us behind the scenes, is handling all of the type conversions automatically. Um, we just type a simple algebraic expression, and Pilot takes care of doing all of the type conversions that are necessary for our result to be correct. Okay. All right. So that's a bit of our deep dive into fixed point math on TTL Computer 2 and Pilot. And I think that's it for today. Until next time, thanks for watching.